Hello, everybody, and welcome to GEOTOP seminar. And this time we are very happy to have Tamas Kalman from Tokyo Institute of Technology and the International Institute for Sustainability with knotted chiral meta-meta, Hiroshima University, talking about knotted and branching defects in ordered media. Tamas, to you.
Thank you very much, Enzo, for the introduction. Thank you very much as well for the invitation. It is my absolute pleasure to be speaking in this oldest online seminar series of the world. So let me get started. So just to give a very quick overview of what is going to happen in this talk. First of all, I should not forget to mention that it's all based on a joint preprint that we put out with Yuta Nozaki, Yuya Koda, and Masakazu Teragaito, three colleagues of mine here in Japan, in which we look at ordered media in some sort of classical three-dimensional setup. In particular, we concentrate on the line defects that can occur in such systems. And what we really do want to pay attention to here is the possibility that these line defects may not be simple curves, but in fact could branch and therefore end up being graphs, such as this kind of drawing right here. So the question that I'm going to look at is what is preserved about such systems? So when they undergo continuous deformations, what other configurations can they become? Are there meaningful invariants here? The result is in a sense kind of negative. It turns out there is not too much topological protection. Specifically, what we find is this. Oops, sorry about that. That two such textures end up being equivalent if and only if their defects, in some sense, which I will explain, generate the same subgroup or perhaps conjugate subgroups within the fundamental group of the order parameter space. That's the kind of result I'm heading to. So let's be specific here. Some of what I say will apply in some sort of general setup, but it's nice to have a concrete example in mind. And for most of this talk, that's going to be biaxial nematic liquid crystals. And as you very well know, this is the kind of physical system in which there exist molecules that can be modeled or approximated by some kind of an ellipse or other shape, which has symmetry. In particular, it has two perpendicular symmetry axes, the molecules do. So you can think of them as kind of being flat, but not circular, rather more like an ellipse with those two symmetry axes. Now, to say something super basic about this kind of system, when you have two of those symmetry axes, then you also get one more for free. The third axis is just going to be perpendicular to the first two. So to describe the position of each molecule, what I would prefer to look at instead of actual molecules is this kind of little local system where there are three perpendicular axes. They are ordered, so I can keep track of which is which, but they are not directed. And that's exactly why this system has sort of enough symmetries to be interesting. So the quaternions are going to pop up very soon. So in my very next page, I'm going to claim that the order parameter space, the set of all possible positions that these molecules can take, is S3, the three-dimensional sphere modeled by the quaternion group. So I thought it might be useful to remind everyone how the quaternions pop up in this context, just in case you haven't thought about this recently. This is all very classic, of course. What happens is that the unit quaternions, of course, form the set S3. The well, is the unit sphere in the set of all quaternions which is isomorphic to R4. Then if you use the unit quaternions, you can act by them on all quaternions by conjugation. Now, one is obviously fixed, therefore it's orthogonal complement, the space of so-called pure quaternions that's also fixed. So now you have your action on R3. That's how this is going to be relevant. Of course, R3 is where these three axes live. Now, if you do a little calculation, it's very simple to see that the actions of the standard units in the quaternion group are degree pi by 180-degree rotations around the usual coordinate axes. Plus or minus 1 actually acts trivially. And these will be the only unit quaternions that leave the three axes fixed. And that's exactly how the set of all possible positions is this whole set of unit quaternions mod out by the quaternion group. Okay, so now that I have said something super classical, I just remember that I should have said a couple of more things on the previous page. Namely, I really should acknowledge that the study we have carried out has a very classical feel to it. Indeed, there is a lot of classical literature, maybe not actually also very recent literature on line defects in ordered media. This goes back at least to the classical and well-known paper of Merlin, and there are also well-known works by Alexander and his collaborators Kimian and Macon. I could go on and list a whole bunch of authors here. So what we are trying to add to this story is this one little thing about the branching. So maybe that's something that hasn't been looked at so much in the literature before. Anyway, just to continue what I was saying. So our order parameter space then is this quotient, S3 mod Q. Q is the quaternion group. The pi one of such a quotient is the group Q itself. There's a fundamental group of order parameter space. That means, as it is very well known, that the possible defects come in various types. There's kind of a bit of richness here to this fundamental group. It has 8 elements. So the types of defects will correspond to the conjugacy classes within that group. Now, in the case of the quaternion group, that's very simple. Well, the unit element, of course, forms a conjugacy class. So does -1 by itself. And there are 3 more formed by just the standard units and their inverses, actually, -1 times. So the defect lines that come in these types cannot end in the bulk. That's a very well-known observation. But in this case, they actually may form branch points. Degree 3 will be the typical case, but it could even be higher. Well, that will be very transient, of course, I realize, but degree 3 is definitely possible and has been observed. Point defects actually do not occur in this system because pi 2 of this quotient space, the order parameter space. Oh, why is this not boldface? Should have been boldface. Sorry about that. Well, that's trivial. Pi 2 is trivial. Therefore, you do not get point defects. You only get these line defects. Now, let me do a little figure up here to try to indicate that there is something sort of nice and interesting going on about these defects and their branching.
Tamas,
So,
I have a question. Oh, is extremely basic. Can you remind me, what does it mean degree 3 for a branch point?
I just did that at this branch point, there will be 3 incident lines so emanating from it.
So the next question is when you say or higher, and then you probably is there any reason to believe that a higher number of branches are unstable or something like this, energetically unstable, or they are just rare?
it's a little hard for me to answer that with 100% certainty, but it definitely seems to me that they will be energetically unstable. So for example, this is, well, degree 4. So such a branch point will tend to move into this configuration.
Oh, I see. Okay.
Under very small perturbations.
Right.
Or into this one.
Sure.
So it will not like being in this sort of unstable configuration.
Okay, thank you.
On the other hand, in one parameter families of these systems, degree 4 points will definitely occur. In fact, that's exactly the kind of thing I'm going to look at when, for example, in this configuration, this middle edge shortens with time, and eventually it contracts down to length 0, and then it reappears, but in the other direction like that. So that will be possible.
Thank
at least
you.
in our model, but as far as I know, that's certainly possible in the real world as well.
Sorry, but in this case with quaternions, since right, if you imagine Renzo, if you imagine two lines coming together, and they each have one of the quaternion charges, like I and J, then the black line that comes out has to be K.
That's exactly what I was going to show you.
Yeah,
okay.
And so suppose you had the thing he drew with three things with 3. Then you could have I and J coming in, and then K would go across, and then I and J would have to come out.
Okay.
He'll show you. I guess I'm sorry. I'm trying to clarify.
That's exactly what I was going to show. So
okay,
let's do it. So indeed, let's say okay. So these I have these axes. I haven't even made up my mind how to associate them to I, J, and K. Doesn't even matter actually. So let's say this defect is one of the 3, either I type, J type, or K type. So what that actually means is that if you travel around this defect and come back to the same vicinity, I will need a little bit more room for it. Let me not go that close, but I kind of come back. So then what happens to my 3 perpendicular axes is that they do return to their original positions. But if I actually put some sort of reminder orientation on them, this is not canonical. That's exactly the point, that it is not canonical. But at the beginning, I put arrows on my axes, and then I continuously extend those arrows to all these configurations along this loop. Then this being the red type corresponding to this red line means that when I return, the red axis is still oriented in the original way, but the other 2 axes flip. That's what it means for this defect to be red type, to correspond to this axis. Now, if I continue this, let's try to do it. I continue my little journey around this neighborhood. Say that I go like this. Now I have encircled a loop of green type. So what that means is that now the green axis acts in a special way. So excuse me, is going to keep its orientation. So here it was oriented to the right, so it's still oriented to the right. However, the other 2 axes will flip their orientations with respect to this. So this green singularity has the effect of flipping the red axis down and the blue axis actually back to the original position. So, and then the next realization is that the concatenation of these 2 little paths, actually little loops, is homotopic to another loop, which does, have I left enough room for myself for that? That's what I want to draw next. I suppose you see what I mean. Going first this way and then this way is homotopic to going around in this way. Therefore, so now let's observe what is supposed to happen along this loop. Well, this configuration turns into this. And what is that? It's a 180-degree rotation around the blue axis. Therefore, from that I know, as it's been already remarked, that the proper color for this axis is blue. It has to be of the third type. So indeed, exactly as you have just heard, if, for example, this is type I, this is type J, or I mean, it's conjugacy class, then this third one is of type K. So that's the kind of phenomenon which we see at these branch points. Okay, so let me go on and say something about how we are going to go about this analysis. So, well, of course, the domain for me is going to be R3. The defect is going to be bounded compact. So I do not allow these defect lines to approach any kind of boundary, even if such things exist in the system. So that's the analysis that I'm about to carry out in this talk. So the defect in my mathematical model then is a finite spatial graph. Of course, its edges can be knotted and linked. It can look pretty complicated and everything. To follow what's going on, we will present these defects with planar diagrams, as is somehow always the case in knot theory. You just cannot get rid of these planar diagrams, but they do have advantages, as you will see in this case as well. And also just to keep track of stuff, edges of the graph will be given reference orientations. Those are totally arbitrary. They have absolutely no physical meaning, but they will be helpful. So then the label of each arc of the projection can be defined not just as a conjugacy class, but as an actual element of Q. So that's kind of a good point to keep in mind. Labels of arcs can be defined as elements of the quaternion group, or well, whatever fundamental group your order parameter space has. And the way that happens is just the standard way. So an arc, I should have maybe said what that means, is, for example, this. That's an arc. So it goes from an undercrossing to another undercrossing. But arcs may also end at vertices when I have vertices in my graph. So this is a different arc from this. Well, except if they somehow connect up and become the same arc, but that's not the typical case. So anyway, as is totally standard, we use some kind of right-hand rule that, so whenever we have an arc with its reference orientation, and we have a base point that we use to define our fundamental group, then we imagine the base point lying like somewhere above the projection plane. And then from that base point, we descend down to the arc, circle around it once using the right-hand rule. So that's why I need the reference orientation, so that I know whether to go around this way or the other way. But apparently, I'm going to prefer, it's too small. I'm going to prefer going around this way if the reference orientation is this. Does it look like the right-hand rule? It looks like that. Okay, good. All right. So then this little thing we did here can be said slightly more abstractly in this way. So if I use this scheme to give actual labels as elements of the quaternion group to each arc, then near a vertex of the graph, the three labels nearby, A, B, and C, satisfy this relation. Okay, this is just a more abstract way of making the exact same observation that we discussed up here. Similar things can be said near crossings. So when two parts of the knotted graph, the spatial graph, appear to cross in the projection, Well, then the 4 nearby labels satisfy this very natural relation, as is completely classical, right? So if you come here, you go under by A, then you follow by B. That's homotopic to first following B and then following A. So that's the relation which you can use to express any of the 4 using the other 3. Okay, and then as I said, my main concern here is what defect configurations can be transformed into what other defect configurations. For example, are these 2 things equivalent or not? So these are actually possible. So if you check, then the labels I put on these oriented arcs do satisfy all those, well, I mean, basically these 2 requirements at every site. In this case, there are, in fact, not vertices, just crossings. All right, so transform. I should say what I mean by transformations. So how do I model this physical situation? Well, okay, so here are all the local possibilities for what can happen to my system. Well, there can be, so isotopies can happen. Well, maybe the diagram simply gets pushed around without changing its combinatorics, but there can also be Reidemeister moves. Well, they can be of the usual knot theory Reidemeister moves, 1 and 2, and do I even have 3? Yeah, here it is. So that can happen, and everything is labeled, and I kept track of the labels here. It gets a little bit complicated sometimes, but never mind. For example, it's of course a very important principle that when you perform a Reidemeister 3 move, then these outer endpoints where the projection leaves the neighborhood in which the move was performed, they keep their labels. These labels are all the same in this case as in this case. All right, but we do consider these vertices, right? So when there is a vertex, it can happen that some other arc of the diagrams, like this arc, slides under that vertex or slides over it. So that can certainly occur in a projection, or as a kind of generalization of Reidemeister 1, this can also happen. So at a vertex, when you have 2 sort of adjacent defect lines emanating from that, and they are kind of indeed adjacent in the projection, then they can actually twist like this or like this. And that too happens in such a way that the outgoing labels do not change. So if the label was A on this arc, then it's still A here as well as here, etc., etc. So I guess it's fairly easy to see that all of this action can take place in my planar projections. But that's not only it. There is more. We do have graphs, and they can do interesting stuff. So, for example, as I have already said, edges can contract. That sounds physically kind of implausible, but in my mathematical model, I will certainly allow such a thing. So, for example, this edge here can contract down to your point. Let me point out here that so the label on this contracting edge is of course determined either by these things, because there is a relation imposed by this vertex, or it in the same way equivalently this same D can be determined from these labels on the other side. Anyway, this is the formula. And finally, I do this kind of mathematical game when some edge with the label 1 can just be arbitrarily introduced into the system. That's because it means nothing, essentially. So the label being 1 means that it's not defected. So it's as if it's not even there. So then, well, I might as well draw it. Anyway, there's no cause for that. So sometimes I would just arbitrarily put some edge with the label 1 into my diagrams. All right. So an important observation about all this is that there is this subgroup of the quaternion group, or whatever our fundamental group is, that is generated by these labels in the diagram. And that subgroup just doesn't change. Subgroup does not change when the moves that I have discussed so far are performed. So that's why I was kind of careful to, for example, point this out. That so, for example, when the system goes from here into this configuration, a new label appears, but that new label is in fact a function of the previous labels. So when you add this new label as a generator of the subgroup, that's not going to give a different subgroup. It's going to generate the exact same as was generated in this situation. And you can go through all this list. It's kind of boring, so let me skip that. But indeed, all these labels that you will see in some short arcs that pop up in these little diagrams, they will all be determined by these outer labels. Therefore, as I said, the subgroup generated by the labels will not change. Well, I should say something about the base point, which is again classical. I'm sure you have heard it. It's probably boring even, but it should be pointed out that to work with the fundamental group, you need to use a base point. And that is because you want to make sense of the product. Otherwise, it's not a group if you cannot multiply things. And to multiply things, well, multiply loops, the loops need to start from and come back to the same start point, and that's the same base point. Well, so we are imagining this base point sort of above our diagram plane, but it's at some finite height. So the moves that I have described so far, well, they describe the changes that happen to our diagrams sort of far below our base point. But that doesn't have to be the case. So some defect line may pass kind of over the base point. You know, I want to follow the deformation of my system far into the future, and who knows, it might decide to sort of go over the base point. So in that case, this labeling system, I mean, when I refined the labels from conjugacy classes of Q to actual elements of Q, so that labeling system breaks down in such moments. Then it's restored after the strand passed over the base point and kind of returned down to rejoin the others down there. The system is restored, but all labels will have been conjugated by the same element of Q. So this will happen to all the labels. CI is one of the labels in my system, corresponding to one of the arcs, is going to get conjugated. By what? So what is this age? Well, probably you all know what it is, but let me maybe say that, well, the way to imagine what this age is kind of to think topologically. So instead of imagining that a defect line passes over the base point, imagine that the base point goes down and tucks under one of the defect lines and then comes back. And that's age, that loop. When the base point goes down, hooks one of the defect lines and comes back. That loop is age, and all labels get conjugated by this age in this instance. Well, so in that case, the subgroup generated by the labels will also get affected, but in a very orderly way. So every one of its elements gets conjugated by the same age. Therefore, the subgroup itself changes into a conjugate subgroup of the fundamental group. So that's a phenomenon. This is certainly possible. Therefore, I need to allow simultaneous conjugations of all the labels in my diagram. Ooh, I really have a lag in this broadcast here. Anyhow, simultaneous conjugations of all labels are allowed. Well, of course, by the same element of Q. what I described is how you can keep track of all the little changes that can happen in your system over time by looking at planar pictures, like projections of the defect configuration. All right, so I'm already at 30 minutes, but maybe I should stop for questions here before I go to state my main result. Well, in case there are no questions, I should state the main result, which is the following. So it turns out, well, that as I explained, the conjugacy class of the subgroup generated by those labels it does not change. So the theorem states that it's actually a complete invariant. So that is to say, if two diagrams, well, if the labels in two diagrams generate the same subgroup, then the two diagrams can actually be deformed into one another. Or if you don't like me talking about diagrams so much, then I can also state the same thing without referring to diagrams in the following way. So if I have my two biaxial nematic liquid crystal textures, and I wonder whether one can be deformed into the other, well, that's true if and only if the defects in both configurations have a complement in three-dimensional space. That complement has a fundamental group, and now each element of that fundamental group is mapped to some element of Q or whatever this group is, and that, well, so the image of that is a subgroup, and that subgroup has to stay the same or has to become conjugate. So it's kind of harder to say this thing without referring to the diagram, but it's important perhaps to point that out too. All right, so as I say this, I'm very conscious of one thing here. So I said conjugate subgroups. So Q doesn't really have conjugate subgroups. I'm going to state that on the next slide. In fact, all subgroups of the quaternion group are only conjugate to themselves. On the other hand, so maybe I shouldn't even have said this part. But on the other hand, basically the same analysis applies for other groups. So, just sort of as mathematical talk, if you can imagine some order parameter space in which the fundamental group is not Q, but some other group, in that case, you would look at subgroups, in fact, at finitely generated subgroups and their conjugacy classes, and the same results will go through. But let me not try to say such general things because they're just sometimes difficult to even discuss. Instead, so let me concretely say what all this means for the classification. So our group Q has 6 subgroups. Each is only conjugate to itself. So therefore, there are 6 types in the system. As I set up my mathematical model, in that model, there are 6 types of defects. Well, maybe there is no defect that corresponds to the trivial subgroup. Maybe there is a single, okay, sorry. So there is some big defect configuration, but in fact, all labels in it are just -1. And then it's going to be equivalent to this very simple configuration. Equivalent under all those moves that I have given you. Well, there is maybe a single case of I, so that's when the subgroup is the one generated by I, or by J, or by K, or maybe you have the entire Q, and as a representative of that case, I chose the theta graph, whatever that is. So I mean, all these things that I've drawn here are not some sort of canonical objects. They are just examples of defect configurations that give rise to the various subgroups. So that's the kind of thing we have. So for example, as a corollary of that, if defects exist at all, then you cannot get rid of them. you can't completely eliminate them because then they would stop generating some non-trivial subgroup. If everything is of type 1, then that will remain, sorry, type -1, then that situation will be stable. You will, other types of defects will not pop up. So if you don't have, well, this is basically, okay, so if you only have I, you don't have J, you don't have K, then again, they will not come into existence later. On the other hand, if T of I, J, and K are present, then at least T of I, J, and K will always be present. That's the sort of corollary that this has. So since I'm not doing so well with time, let me skip this sort of trivial thing I wanted to do here and say something perhaps slightly more interesting here. So, so can these defect lines simply just cross and go through? It seems like there is so much flexibility in this kind of system. So that turns out to be not the case though. So what if I try to resolve this sort of situation? So there are two defect lines, they clasp like that. So what if I try to pull this through? So let me sort of formally use my moves to try and do that. So for example, now I will play this magic trick of introducing two vertices here and connecting them with a defect, which is not a defect because it's going to get the label 1. All right, so the other labels are the same. All right, and then I can contract that down. So of course I could have just done that without worrying so much about this sort of funny fake defect there, but I contracted it down now. So I just kind of want to do this carefully here so that we don't lose track of the precise labels. Hopefully I'm going to do this. So yes, I deformed the system like that. Next. So I will untwist these two kinks. So that's basically the Reidemeister 1 move, which I did allow. So I will just get this configuration. Again, the outgoing arcs do not change their labels. And then finally, I will try to complete my sort of little move here by, sorry, I need a little bit more room for that, by pulling across. So, but that still leaves an edge in there. So, and if you compute the label, which I will call C, of this new edge, it will actually be the commutator of C1 and C2, also B1 and B2, which happen to be the same. So for example, this sort of phenomenon occurs that when you attempt to resolve some clasp, then this kind of wrong vortex appears. It will be trivial if these two labels commute. And in that case, yes, you can just make the two strands cross. I mean, right, to move across each other. On the other hand, if the two labels do not commute, then there will be a price. There will be this extra edge in there. So it's not like you can just totally do anything, but you can do quite a bit. So let me say just super quickly how we do make sure that what I said is true. What I said was this, that the conjugacy class of this generated subgroup is a complete invariant. So just to give you a feel for this, I don't want to bore you with all these details. To prove the non-trivial direction here, I need to take two diagrams, or two textures whose labels generate conjugate subgroups. But then, of course, by a simultaneous conjugation, which was one of my allowed moves, we may assume that the two subgroups are actually the same. Let me call it H. And let me also fix a set of generators for this group H. And then it will suffice for me to transform both of my diagrams to this sort of funny thing. I mean, I realize that this is just a mathematical abstraction here. This is not something a physical system we want to look like, with these extremely many defects coming together in the same point. But that's not the point of my talk, really. I don't claim that exactly this configuration will occur. What I'm trying to explain here is that there is no topological obstruction, no reason to expect that that certain things will be preserved in the system beyond that subgroup generated by all those types of the defects. Anyway, so go back to mathematical talk. What I'm trying to do here is to argue that any diagram where some subgroup is generated can be deformed into this kind of standardized diagram using these kind of little tricks. To do that, first you get rid of all the crossings. That's basically what we did before, in this case up to maybe this point. Here I have drawn the same idea a little bit differently. In any case, you can just formally get rid of all the crossing points of the diagram. And then there is an interesting move here, kind of like a handle slide, which allows to do the following. Oh, I also wanted to say that after getting rid of the crossings in the diagram, you still have a big planar graph. So in that, you can contract edges until there is only one vertex left there. So then it will really start looking like this, but the labels will be totally different. I have no control what the labels will be after doing all those contractions. So how do I standardize the labels? Well, that happens with the following sort of mathematical nonsense. So for each I was the index of the fixed generator for the subgroup H. For each of those, I just sort of add this fake loop of label 1, sort of like here, and then use these interesting kind of transfection moves to change that label 1 to the label CI. Why can I even hope to do so? Well, that is because after I transform my original arbitrary diagram into this kind of flower shape with some labels on those petals, then maybe I observed that those labels generate the same subgroup H as before. Therefore, they also generate all these fixed objects CI. So, so this kind of move here allows me to multiply a nearby label like C onto this adjacent loop whose label is originally X. So after here it is X, but it can become XC. How does that go? Well, so here you do a vertex splitting. So so you get a little edge here. So the label of that is this product, X times C. That's because there is that requirement we talked about that the products around the vertices need to be trivial. Okay, so after that, I'm just going to do isotopy. So I'm going to make this longer and I'm going to make this shorter so that my diagram will look more like this. X, C, and X are still the labels on these edges, all the way until this edge is actually contracted down to a point. And then I have my XC loop and my C loop. The only problem being that that this kind of the C loop followed up the XC loop, and that's not the way I wanted them. But it's possible to entangle them, well, rather to disentangle them by doing a little Reidemeister move here. So just sort of twisting these like that, and then twisting these two like that, and then just doing a regular Reidemeister 2 here. So then eventually you get C and XC. I don't know how close attention you have paid. I'm kind of cheating here, but let me not go into those details because they're not maybe that exciting. So yeah. Here are all the little details that I skipped. So instead, maybe let me add with this slightly more interesting example, just to give you a feel for how, for example, this system is in fact equivalent to this system, which is just my standard representative for the subgroup generated by these, which is the entire quaternion group, because I do have both I and J, and if I have I, then I and J, then I have the product also, which is K, so I basically have everything then. All right, so the way this is supposed to work, like I said, is that I introduce these fake ones. By that, I get rid of these crossings, really. But not quite yet, because I still have crossings here, but those can just be untwisted, and then I don't have crossings anymore at this stage. So then comes this thing when I contract these three edges, all of them, so that my diagram becomes like that. Then I do all this transaction stuff to get it standard like that. And then after that is just basically the reverse. I mean, the same operation in reverse applied to this diagram. So maybe that's not that important now. So with that, I think it's actually time to stop. So thank you very much for your attention.
Okay, Tamas, thank you very much. Interesting, and it's a fascinating example at the end. Any questions, please?
Okay. So I'm reading Randy Canyon's remarks. Okay, I see.
I have a very, again, maybe related to physics. Sorry, Tamas, I just like to hear your comment. I tend to see very often in attempting to apply mathematics to physics, the use of Reidemeister type 1 move, which is of course perfectly fine topologically speaking, but in many physical systems, this move corresponds to either an increase or decrease of some kind of energy. Do you have any comment on that?
Not very, very useful comments, I don't think. So I'm assured by the experts that there are very low energy barriers to all of these moves. But I cannot quite give you the proper answer here because I am absolutely not an experimentalist. I don't have the experience to working with these liquid crystal systems.
Okay.
And whether this is feasible. But Ivan Smoljuk and others assured me that yes, these systems are quite flexible and can undergo all of these changes easily.
Sure. Maybe, I don't know if Randy is still with us. Maybe he has a comment on that. I have, do you have, I mean, do you have any project to apply this piece of mathematics to actual defects in nematics?
Well, that's work into. So that's that such a thing would be one of the aims of this institute, whose entire name you read out at the beginning.
Exactly. Yes.
So indeed, we have carried out this little analysis with the aim of finding applications for it.
Right.
Seeing what kind of cool system we can build out of, say, biaxial nematics. I can't quite say yet that we have succeeded in that, but we are thinking about it.
Okay. Well, if there are no questions, I thank you again, Tamas. Thank you. Thank you so much for this interesting talk. Thank you.
Thank you very much for your attention.